Very well, we're going to have a look at the fundamental theorem of arithmetic. It is a theorem of vast importance and interest, and it has a beautifully simple proof. So let's have a look at it together now. The claim is that let A be a natural number and let A be greater than 1. Then there exist pairwise distinct or just distinct primes P1 through Pn and exponents K1 through Kn such that A is equal to its factorization P1 to K1 multiplied by P2 to K2 times ... times Pn to Kn, or in a more compact form, the product ranging through 1 to n of Pi to Ki. Proof. And of course, we also say that this is a unique decomposition. So let's add it to the claim. This decomposition or factorization is unique up to the order of Pi, well, P1, P2, Pn. They could be jumbled up, they could be in a different order, it would be still the same factorization. Up to the order, it is unique. So we shall split the proof, which is trivial, into two sections. First, we shall prove the existence of such factorization for all natural numbers greater than 1, and then we shall have a look at the uniqueness, which is, in a way, a much more interesting aspect of the theorem, but the existence is no less interesting. Existence. We shall lead the proof by contradiction. Assume that A is the smallest natural number possible such that it does not have a factorization. Well, what can we deduce from this? If A does not have a factorization, well, that means that A is not prime itself, because otherwise A itself would be its own factorization. So A is not prime. This means that A may be written as the product of at least two other integers, say B times C. But we have assumed that A is the smallest possible number which does not have factorization. Naturally, B and C are smaller than A. Well, actually, just strictly smaller, because neither of them can be 1, because A is not prime. BC are strictly smaller than A. This means, since A is the smallest number without factorization that B, C indeed have factorization. But then A also has a factorization. Namely, it is the factorization of B times the factorization of C. And as such, we arrive at a contradiction. Uniqueness now. Well, again, let A be the smallest number with two factorizations. Namely, A is equal to the product of Pi to Ki. I is ranging through 1 to n, and that is equal to the product of I ranging through 1 to n of some Qi, Ki. Now it is time to use our magic tool which we have prepared earlier, the fundamental theorem of arithmetic lemma. Now, we know that given some j, which is an index between 1 and n, Pj divides A. Indeed, it is in the factorization of A, so it makes sense that it divides it. But this, of course, means also that this Pj also divides the other form, because there is equality, A is equal to this, the other factorization. But this means that there exists some L in n such that Pj divides QL. But of course, Q is a prime, and so is P. So this means that Pj is indeed equal to QL. We also observe that since J was chosen arbitrarily, this holds for all of them. And what more, since all of the primes in the factorization are distinct, we have a one-to-one correspondence. This means then that for all I, Pi is equal to Q by I, where pi is some permutation. But this, of course, means simply that the two factorizations are equal up to the order of the factors. This completes the proof. Oh, one last thing. The Pi's and Qi's do not necessarily have the same exponent. That was a mistake on my part. Nevertheless, my argument was not based on it, so it doesn't matter. That is all.